video is on page 3 of the Unit 12 notes, and the goal of this section of the video is to provide for you some reminders about basic, very simple acid-base reactions and writing them as net ionic equations. In this video, only those acids and bases that are strong are going to be identified. So some of this is going to be left blank. All right. As we take a look, the very first one, if you notice, happens to be what should be a single replacement reaction. So again, remind yourself that in this chapter, you're going to end up doing some of these reactions. And we want to review all of that. So this would be something that you might see on a test. The very first thing that you want to do is we're going to be skipping some steps now. So as we read through the piece of magnesium ribbon, the magnesium ribbon is just a solid, so we'll leave that as Mg. And then our hydrochloric acid, we should now know that it is a strong acid. And because it's a strong acid, I'm immediately now going to start writing it as ions. Again, it's a single replacement reaction. So if you remember, the whole goal of that would be to take your two similar type ions, so in this case positive type ions, and replace each other. That therefore means that we're going to end up with magnesium turning into an ion. We're going to be left with some chloride ions. And now our hydrogen ion is going to turn into hydrogen gas. That therefore means that chloride will be a spectator. So we can immediately remove the chlorides. And once we've done that, we now have a net ionic equation. The other label besides single replacement is, do notice that this is also a redox reaction. So while it's an acid reaction, it's a single replacement reaction, it's also a redox reaction. They are all one and the same. As we look at the next one, this is a reaction that some of you guys have had difficulty with, in the sense that it too is going to be a single replacement reaction. In this case, we're going to go ahead and take a solid piece of sodium metal, and we're going to just dump it into water. Now, keep in mind, water, which I'm writing in green because it's neutral, is really a hydrogen ion that is joined to a hydroxide ion. And when you're working with acids and bases, you want to remind yourself of that. So as we look at this, what ends up happening is, again, the sodium ion, which has a similar capability as the hydrogen, both being positive type ions, will be able to replace each other. Again, sodium isn't an ion yet, but as we write it over on the product side, we're going to turn it into an ion. So there it is, sodium ions. Along with those sodium ions, the hydroxide ion is going to be left behind. Notice it's blue because it's a base. Now if you check it and you want to just see, sodium hydroxide is not just a base, but it's a strong base. So should I leave these two as ions? Absolutely. And then again, the last thing that we're going to make happens to be converting that hydrogen ion into the hydrogen gas. So again, as I clean up my reaction, I actually have no spectators. I'm going to get rid of that water, and I'm going to have Na plus water yields Na pluses plus OH minuses and hydrogens. Ladies and gents, one more time. This is a single replacement reaction. It's also a redox reaction because, again, your sodium and your hydrogens switch their ions. Our next reaction involves an acid with a metal oxide. This is going to be double replacement. Now, because this particular video is solely about acids and bases that are considered strong, notice what I am about to avoid. That is the fact that as we look at hydrocyanic acid, we notice that that is definitely not a strong acid. So because of that, we're going to go ahead and leave that behind. Let's look at our next one. the infamous acid carbonate reaction. It's an acid carbonate. One more time, ladies and gents, if you see an H2CO3 as a product, chances are you're thinking correctly, but you really need to convert it into CO2 and H2O. Its ability to decompose is very easy. So as we take a look one more time, we're going to read through and we see that we have sulfuric acid, which is highly soluble and highly dissociated since it is a strong acid. We also have some calcium carbonate. And if I recollect, even if it's a solution, we are not going to have much ion. So the fact that we're saying it's a calcium carbonate, we're assuming that it's a saturated solution. It's not very soluble. And since it's not very soluble, we are going to accept the fact that there are probably some ions present, and it is the ions that are reacting. Once we have that, hopefully you see that the calcium and the sulfate ions are going to go ahead and precipitate. So here is our solid, which will fall out of solution and hopefully just settle down at the bottom. And then again, folks, we want that water to be one of our products. And we, of course, want that carbon dioxide. We want to see those bubbles because that's going to be the gas that's going to indicate that this reaction is going to try to go as far to the right as possible. All right, the similar case is going to happen with your next reaction, but again, we're going to hold off on this one right now because that nitrous acid happens to be a weak acid, right? We're not referring to nitric acid, we're referring to nitrous. Let's go on to the next one. With the acid-base reactions, this now really starts getting into some of the reactions that you're going to be encountering as you start doing calculations. And that's what we have here. This is your double replacement, but not just a double replacement, it's an actual neutralization. And there are a number of different forms of neutralization. This one is the easiest one to see, and that's because it's physically making the water. That physical creation of water means that you're making the solution as neutral as possible, removing as many hydrogen ions from the acid and as many hydroxide ions from the base as you can. We're going to look at just the first one because we have here hydrobromic acid, a nice strong acid, and we also have here lithium hydroxide, a really strong base. So we're putting both of them into solution, and then we're mixing those two solutions together. As you take a look, the first thing you should notice is that, again, neutralization is going to imply whatever is the acidic and basic properties of each of these species are going to try to react with each other. In this case, that reaction will create water. The other two ions will again attempt to react with each other. But if we were to put lithium bromide together, we would see that this is highly soluble. Both halogens as well as alkaline ions are ridiculously soluble. So because of that, we're going to go ahead and we're going to keep those separated. And having kept those separated, we see that the bromide as well as the lithium are spectators. And lo and behold, hydrogen ions are reacting with hydroxides to make as much water as possible. All right, we are also going to do these next two, and this is because these are synthesis reactions. I know that you guys never believe us when we tell you that they are, but the very first thing that you do want to notice is the very simple fact that in these synthesis reactions, you are taking an oxide, in one case a nonmetal oxide, and reacting it with an oxide, water. In the other case, you are taking an oxide, a metal oxide, and also reacting with an oxide, water. So in both cases, if you have two reactants where they are both oxides, you then know that you need to be making a synthesis reaction. In this case, join your sulfur trioxide. It happens to be bubbled, so it's a gas. It's also covalent, so no ions are on it. And you're going to bubble it into water. When you bubble it into water, go ahead and line it up. It should always be whatever element is furthest to the left. Hydrogen. How many are there? The nonmetal, sulfur. How many are there? The oxygens are always last. How many are there? And you are literally adding the subscripts from your reactants. That's the easiest way to do these. Once in a while they're different, but that is the easiest. You're then going to look at the thing that you have created, which in this case is an acid, and you're going to decide that that is a strong acid. Sulfuric acid is, of course, strong. Separate it out. If it weren't a strong acid, you wouldn't do that step, but since it is, we're leaving it like that. One more, and again, this is going to involve an oxide, solid barium oxide, and water. Here's our water. Here's our solid barium oxide. And again, folks, what you want to try to do is take the element that is furthest to the left. In this case, it would be the metallic ion, barium. You want to then join it with as many hydroxides as possible. Now, you might ask why. The very simple reason is because I have O's and I have H's, and I need to make some sort of ion over here that would go with the barium positive ion. So that's going to be my hydroxide ion. Notice there are 2 hydrogens and 2 oxygens, which means really it's barium hydroxide. Again, take a look at that formula. That is a nice strong base. Let's go ahead. When it's in solution, it is going to exist solely as ions. So this is not going to be present, but barium ions and hydroxide ions will be. And ladies and gents, that does conclude